Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so let's get started. Welcome to the MIC public seminar. I'm Zhengyou Zhang, research manager of the Multimedia Interaction and Communication Group. So this is a part of our group's public seminar series. So this is a tradition started by Phil. The idea is to give you internal talks before we present to the external world. So we think this is a good chance to practice also for us. So today we have 4 mini talks. Those talks will be presented in about 2 weeks at the IEEE International Workshop on Multimedia Signal Processing. And we'll have 4 talks. First, Dinei will give the first one, and then Sanjeev will give the next 2 talks, and I will give the last one. Dinei, so let's just go.
All right, so thanks for the introduction. So I've been presenting our work in crowdsourcing for determining a region of interest in video, and this is joint work with Flavio Ribeiro at University of São Paulo. So the first is like crowdsourcing has attracted a lot of attention, and crowdsourcing, exactly what is crowdsourcing? So it's essentially the idea of actually using a crowd, using a large number of people to actually achieve some purpose, and that purpose could be like funding or could be like building some knowledge. And essentially the crowdsourcing is like has been there for a while, but with the event of the internet, it's much easier to achieve and to reach a much higher number of people. So very successful examples of that is wikis and things like Wikipedia is like a very huge phenomenon. Crowdfunding, where you actually apply to the community and say we want to fund some specific project or anything, and then you actually collect like a small amounts for a number of people. We are more interested in particular what we want to call human computation, which is the idea of using humans to do processing tasks which are not easy for computers to do. And in particular, you're trying to do that with crowdsourcing, right? So what are the benefits of actually doing that? First, scalability. You can actually get very large crowds and recruit and dismiss that very quickly. So if you need like 1,000 people for 5 minutes each, it's like it would be essentially a huge operation to do this in real life. If you can actually do that through crowdsourcing using the web, you can actually get the 1,000 people and dismiss them in 5 minutes very, very easily. Typically, the cost ends up being below market wages, in particular because of this facility of the recruiting and dismissing of that. And you can recruit like a very diverse workforce. So there's a number of reasons. It's a very simple, scalable, cost-effective way of actually getting people to work on particular tasks for you. So the most widespread, the most common platform for crowdsourcing is the Amazon Mechanical Turk, which was launched in 2005, has about 500,000 people registered. And at any time, there's like 50 to 100,000 tasks offered there, available for people to actually take those tasks and do. So the typical human intelligence tasks, as they call, like HITs, are typically very simple tasks, preferably fitting in a page, and requires like typical 1 or 2 minutes to perform. And typically, you're going to be paying like 5 to 25 minutes, 5 to 25 cents per that task. So Microsoft has now an internal offering in crowdsourcing, which is what we call like the Universal Human Relevance System, which actually we've been using right now just for internal things. So we're actually using that for a lot of work relating to search and relating to some of the other things. But that's a a recent offering from Microsoft and it's being mostly used internally right now. So we have done some previous work on crowdsourcing, and that's essentially been the idea of using the crowdsourcing to actually do more studies. So when you're doing like mean opinion scores, like subjective testings of audio and other things, we actually need to ask people. So typically you bring people to the lab, do some experiment, ask their opinions and so on. So we're trying to test on these two previous work, one applied to audio and speech, the other one applied to image, essentially to reproduce that without the controlled environment of the lab. So essentially just recruit workers from the mechanical Turk, have them rate the files the same way that someone would rate at the lab, except that you do not have the control. You do not know if they are the right distance from the screen, if they have the correct headphones, and so on. And then find ways to actually filter that process and get the results you would get from a more controlled study. So essentially the results were pretty encouraging. We essentially can get pretty much the same quality that you would get from a lab study, and with a much faster and lower cost than you would get. So, however, that is very batch sort of processing. So the idea there was like there's this study in the lab, and I want you to do that study using crowdsourcing. But it's like a task, and the end is the end of the task, which is a number. Right? So our vision in that was more tightly integrated. So it's like, can we use human computation as a processing block? So I have like some algorithm, and there is some particular piece of that algorithm which is hard for the computer to do, and then we use like crowdsourcing for that. And then essentially for that, the delay has to be much smaller, and the task has to be a task that can actually, that fits into this process. It's like a processing sort of task. So in order to try to go in that direction, we essentially have like this particular work, which is trying to find region of interest in video. So when you have a video code, and we haven't done that part, so that's what's in future work here. So if you have like a video codec where you're actually going to use region of interest, you're going to use the parts of the video which are more relevant, and the parts of the video where people actually look at, and then put more bits there as opposed to the rest of the video, then you need to know which parts of the video are those parts that are of interest, right? So the problem is that doing that by automatic means is very hard. And essentially, we're going to see a few examples later, but it's like it's very hard to actually figure out what's important or not in a piece of video. So one way of doing that is asking people. So if you ask people to actually watch a movie, and that's the traditional way it's done. So you actually get people, put the movie in front of them, and put on an eye tracker, and then you see what they're looking at. And then, okay, so if people are looking here, so that's the place most people are looking at, so that's where we have to put the bits, right? However, that requires the same thing, bringing people in the lab and then having them with an eye tracker, which costs like $20,000 or so, and then going on.
For that application, does the screen have to be big enough? Because if it's a small screen, can you figure out where I'm looking? It probably doesn't matter.
Yes and no. So the bigger the angle of view, right? The bigger that, the more your human vision system will decay. So yes, there would be more difference. If what you're looking at is very small, then probably the resolution of your eye all fits in the fovea, then there isn't much to do, yes. But typically, so for HDTV kind of scenarios, and even for most of the PC viewing thing, there's actually almost like a 30-degree field of view, which is actually very significant. So essentially what we wanted was like, well, if we can do that in a video, say you have like your YouTube video, for example. So someone upload a video, and then you want to optimize the coding for that thing. So I get that video, I can actually, for example, crowdsource this thing and get what people are looking at, and then insert that into your video coding, and then recode that video with that particular result of that thing, right? So let me do an experiment. So the problem is like, well, okay, so I need to know where people are looking at, and the problem is in the lab we use an eye tracker, but people at home don't have an eye tracker, and I cannot provide them with an eye tracker. So how do I make that part? How do I make you at home figure out where you're looking at? And how do I force you to tell me? So essentially we say, well, okay, we could ask people to point with the mouse, like I'm looking here, right? But then it's like, how do I force you to actually do that, and how do I guarantee that you do? So essentially what we try to do is like, well, okay, so if this is like a video, and I want you to know where you're looking at. Then we can do an experiment, and probably like the people in the back, exactly for the reason Sanjeev was mentioning, the people in the back are not going to get the same impression. But what I want you is to look at this particular eye of the squirrel, right? So we look at that particular eye, and don't look anywhere else. So look at the right eye of the led squirrel, and then if you look in there, and I do this, so what happened is the image changed. You can see that the image changed, but it didn't hurt your eye, right? Now let's do the same thing and look at this squirrel eye, and then keep looking at only that squirrel eye. And I'm going to toggle between the same two slides that I did before. So essentially, if you're looking at that, it's like you don't want to look there, right? So essentially, the idea is what we're doing here is we sort of simulating the visual blur that's typical for the human visual system, which has like this gradual blur. So wherever you're looking at, you have like full resolution, and the resolution sort of diminishes across that. So if we simulate the same response with a filter, so essentially if I sort of blur the image as you go from the point you're looking at, and you're looking at that point, then it doesn't make that much difference. However, if you're trying to look somewhere else, then it actually bothers you. And then by bringing the mouse to this position, you would actually be able to actually look at that and wouldn't sort of hurt your eye. So it's a very intuitive and thing. So the problem is that actually, if we could do that in real time, then that would be very nice. You can just move the mouse there, except for the constraints that we actually have for the system, which essentially means that if you have to play that on a flash player, it actually doesn't work. Because I would have to do this filtering in real time. So what we actually do is an approximation of that, which is actually what we saw in the previous slide, which is we actually compute like a blurred image and a unblurred, the original image and a blurred image by a 10 by 10 box. And then we use like an exponential alpha blending between those two images. So essentially we're not progressively blurring more, we're essentially doing alpha mapping between a blurred and unblurred thing. So essentially we can actually do that in real time as long as the video is not too big. So for a 640 by 360 at 24 frames per second, can actually get that on a 2.5 gigahertz. And we actually deploy that, and we actually measure the frame rate and the frame drops in the users in this thing. So it turns out that about like 10% of the workers experience some frame drops. So there's a limit which you actually say, well, if you have too many frame drops, you just stop, say, well, your computer is not fast enough, we can't do this task. But even one single drop, and that happened to about like one user, as I recall, but otherwise like less than 10% of users got any frame drops at all. So essentially paid like 25 cents to actually do a hit, which turns out to be about like $5 per hour. And then we have to filter those results. First, we have to filter for random results, someone just like do any junk. And we have to filter for the detraction. So a lot of times you start looking at something else and just don't move the mouse or you look at anywhere else. And that also happens with the eye tracker. So when we're actually doing the eye tracker, so on our eye tracker experiment, the screen is not using the full screen. And sometimes people will look at outside the LCD display, which is actually expected. So we also want to get like how good results can we actually get this? How quickly can they follow the point of interest with the mouse? So we actually did an experiment, which is essentially this. So we asked them to actually track that ball, and then we move the ball at random places and see how long they actually take to actually get there. And what we're trying to do is to estimate the delay. So how long after you move your eye to a point of interest, how long it takes for you to actually move the mouse there. And in this case, there's no question. We know there's only one thing to look at the screen, right? So you know what you're supposed to do. So these are the results that we actually get. So actually you can see here, so the black bar, the black line is actually the ground truth. So people essentially take sort of almost a reasonably constant delay. Some people overshoot, some people undershoot the motion to the correct place, right? And when actually average them and then compensate for the average delay, so you shift this by the average delay and then you average all the things, it turns out that the accuracy is actually very impressive, right? So you can actually see that the number of people who overshoot and undershoot is probably about the same. So when you average, you actually get very good results. Yes?
Just a quick question. So the ground truth result is that a red ball?
Yes.
Okay.
Yes.
Should you manipulate use mouse to do it?
Yeah. Yeah, so things like when the circle moves here, you're going to have to move the mouse quickly. So you're trying to move the mouse as quickly as possible to the point you're looking at. And some people will...
The eyes are actually quicker than the mouse.
Yes, yes. So essentially, this is the... So there's experiments that actually show that we spend about like 100 to 150 milliseconds to actually look at some other point. So when you actually have something... So you see something moving here, and then your eyes sort of try to track that. And it takes about 100 to 150 milliseconds. So it turns out that what's going on here is that your eye first see that ball, and then you move the mouse, right? So you're taking another like 300 to 400 milliseconds extra to actually move the mouse there. So that one is about like 15 subjects. And the same with this one.
Use touch screen, it's quicker.
Yeah. Oh, but the touch screen is like you don't want to have your finger, right? And then it will require people to have the touch screen at home, right? Which is not always. Another experiment we wanted to do was like, well, okay, so that was sort of different in the sense that I moved the ball to a random place and then you have to track. But if you can actually, in a movie, a lot of times things are moving, right? So can you actually track the thing when it's moving? And this is the experiment. So this is the experiment we did. So the ball now is just moving at constant speed and then changing directions. And then we say, well, okay, how can you actually compensate? Because then now you know that the ball is going to move in that direction, and can you actually compensate, right? So in this experiment, actually, as you can see here, is like the people did much better. So the delay, the average delay is actually 70 milliseconds. So essentially, there's essentially no delay. And again, when you average the results, you actually get very, very good results on the thing. Okay, so those two are like toy examples. So can we get a better toy example, which might still be a toy example, but like I think was more useful, more typical of some of the scenarios we're looking at. So we did another experiment with a movie trailer, which is the Ice Age 3. So it's a 2.5-minute trailer, and then we did two experiments. We did the same experiment that I was describing before, which actually deployed this on the web. People actually tried to track with the mouse. And we actually had 40 workers actually running that. And then we get like 12 volunteers and actually bring them into the lab with an eye tracker. And some of the volunteers are actually here. So for comparison, keeping the people to the lab and stuff, in this particular case, would take about like 4 hours total person time. And the Turk experiment takes about like $10. So thanks from the people for the usability lab for the help with that. And here's the thing. So what I'm going to show is that I'm going to try to synchronize the two. But the upper one will have the mechanical Turk results, and the bottom one has the eye tracking results. So the balls, essentially, each of these balls represent where someone is actually looking at. Right?
As long as you live, someone who loves you tender.
Okay, so I think most of you actually have actually seen the trailer, so I'm gonna stop the trailer. But I wanted to show actually one thing here. Actually, I'll go back to that in a sec. So let me show what else is interesting here. So this is one particular frame, except I'm doing a different plot of the circle, so you actually can see what actually people are looking at more easily. So in this particular frame, as you saw from this story, I don't know if I played to this point, but it's like they start fighting for the nut, right? And then because of the storyline, actually, the storyline starts with him and then switches like to what they're fighting for and there. And then at this particular frame, there's still like a change between them. And some people are actually going to be looking here. Some people are going to be looking at the other squirrel. Some people are going to be looking at the nut. And essentially, so when people try to do region of interest automatic computer thing, essentially you're trying to look at the frame, right? So you cannot look at the story. So essentially, it's like you're never going to be able to figure out exactly where the story is shifting, where the focus of the story is shifting, right? So, and that's actually important because of two reasons. First, we can actually refine and use this as an upper layer on something that's like, okay, so there's something here which is interesting, and what exactly is interesting, that one, you can actually use some computer vision, some salience estimation to actually figure out what exactly is looking at. So this is some results on what the X and Y position by using, on exactly that clip, by using the mechanical Chirk and by using the eye tracker. And you can see a number of things. The first one is the mechanical Chirk result seems cleaner, right? So if you look at this and you look at the amount of noise, essentially, regarding each of these, you're going to conclude that the eye tracker actually has more noise. So this actually has two reasons. First, the eye tracker does have more noise. Second, like moving your mouse is harder than actually moving your eye. So moving your eye is much more natural. And and actually brings me to one point I wanted to show on that video, which is, so the only place that actually there is a difference, significant difference, is, hold on. So if you look at this particular frame, I'm not going to spend the time on the other one, but it's like the story actually tells that the squirrel is looking at something, and then you can actually see that the people on the eye tracker, they try to see what the squirrel is looking at, but they look and there is nothing, right? So it turns out that people who actually mouth with the mouse, they actually, when they look at something, you keep looking at different places. When you look at something and there's nothing there, you actually don't move the mouse there. So that actually was the one place. So this is one place actually significantly different, which is not necessarily bad, but essentially it's like when you look at something and then you look and there's nothing, you don't move the mouse there. So that was one of the conclusions. So essentially, we can actually do the region of interest determination at a reasonably low cost and very quickly, so you don't have to assemble and disassemble everyone. The quality overall is good, and there are some differences, as I just point out, particularly in these instinctive saccades when you actually look at something and then come back to the thing, which are a lot of times distractions and stuff. And there's there's a small delay on moving the mouse. And as I said before, it can actually be combined with other salience modeling. So that's essentially the thing. And if you have any questions.
I think when the studios reformat a widescreen format to 4:3, they have to determine region of interest. I don't think they just chop it off, because in many scenes the director wants you to look at something and everything else is in the background and it may not be in the center. But there the region of interest is much bigger, right? The 4:3 as a fraction of the 16:9. So can those scenarios be automated? I guess it's mostly done manually currently.
Yes, so it could be automated. It's probably not the target prime for that, because typically when you're actually coding a DVD, like an actual commercial DVD product, actually paying like a professional to actually see what's the best framing is probably more reliable and probably give better results than actually try to crowdsource that. So I think other applications which are either like lower volume, so you're going to use this in like a lower volume kind of thing instead of printing like millions of DVD copies.
What I was trying to ask is, so when the region of interest is much bigger, do automated techniques work? So I think here you are trying to pinpoint a very narrow region of interest.
It should, because essentially you can't really look at, you typically just look at one place. So what's going to happen is that if you have, and this is one of the examples on what you're talking about, which is hard to frame, which is like, for example, there's a dialogue, and the director put them like in the very opposite corners, right? So what would happen is that if you actually use this, some people are going to be looking here, and they were going to put the mouse there. And then as other people are going to be looking at the other person. So in a dialogue, they would be moving back and forth, right? So you would know that some people are looking at this side of the screen, some people are looking at that side of the screen. Therefore, it's hard to cut either one, right? But the final decision, what I was saying about the professional kind of things, the final decision is like, well, okay, people are looking at both sides of the screen. What do I do then? That decision requires some professional sort of thing, right? So that's. But yeah, you would know that people are looking at both sides, which means that if everyone is looking at one side, then you know you can chop off the other side, right? But if not, then it doesn't tell you what to do.
So how different are the results you get from eye tracking versus automated results, like just using foreground background segmentation or motion detection?
Yeah, so typically, typically you can get some results from automated, and there's a lot of research on sort of trying to get that. The problem with that, of those automated salience detection, region of interest things, is that they can't follow the storyline, and that's what I was trying to say here, right? So a lot of times, like, all they can do is like, well, they can say, well, this looks like relevant, and they do a lot of focal kind of thing, right? So they know that everything that's blurred, so if this is blurred, that's probably not of interest, right? But then they would not be able to actually tell you where the focus of interest is as the story progresses, right? So and that's one of the things. But as I said, it's like one of the things that would be relevant is actually to combine that with some those lower level techniques to actually see, well, on this region, what exactly is the interesting thing.
Information explored during this
experiment? So when we did those two experiments, we were trying to figure out, like, well, okay, so when there's a saccade, what's the delay and can we track? And what we concluded was exactly that those two times are different, right? So when you're tracking something, you can actually compensate for that. So we would need a better modeling of what's actually going on, right? So, and then, yes, if you actually do the modeling, you would actually, we didn't do that, but it's like you would figure out, like, well, by the speed you're moving the mouse, I know you're not looking, you're just moving somewhere else, and then I assume that the delay is going to be the delay that we got, like the 500 millisecond delay, right? If you're actually moving the mouse continuously, then I know you're actually tracking something, so the delay is probably 70 milliseconds or so delay. But we haven't actually done it. So if the delay was like more uniform, then it was easy just to shift. But we didn't. The other things, like the eye tracker results also has a delay, because they actually have to do some filtering, because the initial result is very noisy, right? And then they do some smoothing, which means it also has a delay. And it's also hard to, we didn't do the experiment with the balls and stuff with the eye tracker, so we don't know what the delay is, but we know that there is a delay.
Okay, thank you, Dinei. Actually, I forgot to introduce Dinei. Dinei is a researcher here, and he has done a lot of work from audio, video, image, and to security. And he was a technical co-chair of ICME this year, 2011. So next, Sanjeev will talk. Which one you want to start? Yeah, you can start.
Okay.
And Sanjeev is a principal software architect here. He was a dev manager of Windows Media Group, in charge of audio codec.
Yes. Hello, good morning. So I'm going to start with this talk, the first one. And the first one is regarding basically audio spatialization. And the technology that I'm going to present here is basically a method to do low complexity audio spatialization and allow you to arbitrarily place sounds at various locations within a given environment. And the main idea of audio spatialization is you want to create a virtual environment in a real environment. So I'm in this environment, but I want to, when I hear something, I want to hear like I'm hearing in some other virtual environment. And this type of technology is very useful for, and it's actually becoming more and more useful these days, because one example is multi-party video conferencing, where you have 4 or 5 people, you want to place them around the table, and you can watch them around the table, but you should also be able to hear them from where they're seated on the table. And another example, of course, is immersive games, where you want the player to feel like they're in another environment, and the sounds that they hear should be coming from particular locations. And here's a simple example. You have a table, and so the bottom circle is essentially the listener. And those 2 red dots are the listener's ears, left ear and right ear. And you essentially have, let's say, 3 sources, one labeled 1, 2, 3, and they're seated around the table. And essentially, you want to find the sound at 2 virtual locations, which are going to be the left ear and the right ear. And of course, so this is the virtual environment you wish to recreate. And the real environment that you're using to play back can be different, of course. So in the simple case, you could just have a single listener listening on headphones. And this is the simplest case, of course, to, that's the real environment. And you can also have more complicated environments where you essentially have, let's say, 2 loudspeakers, and the listener is sitting far away, and these are essentially like, the problem of spatializing the audio to these virtual locations, and then the sort of the inverse problem to that is, given the real environment, how do you play back the sounds to so that it sounds correct at these real locations? And essentially, this is audio spatialization, and then this can be like crosstalk cancellation, where you want to cancel, because this loudspeaker is going to go to both the ears, and it's going to travel through some path, and you want to kind of invert that path. So the overall process when you want to create this virtual environment in a real environment is sort of to, invert the real environment and do the forward transform on the virtual environment. And both of these essentially are going to use, similar technologies, except in one case you're doing the inverse, the other you're doing the forward. And the main thing here is that the sound is essentially, people think of this as kind of 2 components. So the sound is going to travel through the room, and there's the room response, which is how the sound travels from one point to another point. And this is essentially, this is kind of the room impulse response, where the sound travels from one point to another, and there's multiple components there, the direct path, and then the sound is going to reflect off the walls, and then it's going to keep reflecting and decaying, and the late reflections, and then you essentially just have like the room reverberation. And the other portion, of course, is the, how a sound from some location differs when it goes to the left ear or to the right ear. And this is the head-related impulse response, or the head-related transfer function. And typically you can definitely measure both of these. So the head-related transfer function is always typically measured. And the room impulse response can be either measured, or it can be kind of just modeled given the room geometry. And this is the way people have been typically doing it, breaking it up into the room impulse response and the head-related transfer function. And Wei-ge and Zhengyou had presented some work a couple years ago on, instead of breaking it up into 2 components, the room impulse response and the head-related impulse response, you can alternatively just measure the combined response using a dummy head. So you can place like a dummy head in a particular room, put microphones in the ears, and play sound from various locations, and you can essentially measure the impulse response to each of the 2 ears. And this is similar to how you measure HRTFs, which is you place the listener in a particular location, and you kind of put the sound at a certain distance from the listener and at various angles, and just kind of measure what you're hearing. And so the difference, of course, is that in this case, the combined response is not just a function of the source location and the orientation, but it's also a function of the listener position. But of course, we can make a simplification, which is to assume that only the relative distance and orientation between the source and listener matter. So if the sound source is located some distance d at an angle theta from the listener, we kind of assume that this is similar to, so both of these have similar response. And we can probably relax this simplification also, but this makes it easier to measure. It makes you have to measure at a fewer number of positions. Otherwise, you have to also change the listener position. Yes?
This relationship is certainly true if you are talking about basic head-related transfer function. When you basically combine room response,
yes.
How how this approximation still holds, or how good is the approximation? Room is considered.
So I think it holds true for of course the direct path, right? So let's say in HRTF you actually measure without a room, essentially, right? And probably for the late reflections and the eventual room reverberation, it doesn't matter much either, because that's basically just, yeah. So I think it matters the most for probably the early reflections. But I think if you're concerned primarily with locating where the sound source is, that's more related to the HRTF, right? And it's kind of like, yeah, essentially you're moving and the sound source is moving. So that's kind of the effect you would get. So if you shift 2 meters to the right and I also shift 2 meters to the right, probably how you hear me within this room won't change that much. Unless you're like very close to a wall or something.
What are you trying to capture?
So basically what we're trying to do is we're trying to minimize the number of positions that we have to capture this response.
I know, but there's 3 things, right? Direct path,
yes.
Doesn't matter the room.
Yes.
The reverberation, you can capture in other ways.
Right.
So the only thing that really matters, the room itself, is the early reflections, but those are not constant when we change. So
right. So what they're being measured here is for a given location in a given room. So it's you can definitely measure it for, like, let's say for this room I can measure me moving around the room as well, right? But I think if the room is pretty large, then I think it matters more if you're closer to the actual reflecting surfaces, right? So of course the main issue with measuring HRTF and this combined head and room impulse response is that you can only you can place the listener at a particular location, but you can only measure this by moving the source at various locations. So let's say I measure I place the source here and I measure the response, and but then of course the source can be at a different location, right? So natural thing is you can do interpolation from the points that you've measured close by, right? And there's actually theoretical results to show, how this spacing should be done so that the interpolation is sort of perfect, using some sort of sync interpolator. But so you can actually, limit the number of measurements pretty significantly. But then the interpolation that's needed to do the reconstruction is essentially a sync interpolator to do the perfect reconstruction. So there's many simplifications you can do to do the interpolation. So one is, of course, you can just interpolate the impulse responses in time domain. But doing that without any other processing is not good because there's different delays, right? So you may essentially, if two responses are off by 180 degrees, you essentially just cancel them to 0. So the way people typically do is they try to align two impulse responses that you're using to do the interpolation. And then once you do the alignment, you can do the linear interpolation. And doing temporal alignment in the time domain has several issues. One, of course, is that it assumes that that the response is linear phase, meaning that all frequency components are shifted by exactly the same amount. And there's, of course, complexity in determining the alignment amount. So we're essentially going to do frequency domain interpolation. So for each of these impulse responses, we can take the transform, right, and do interpolation in the frequency domain. And of course, when you're doing interpolation in the frequency domain, you can, let's say you're interpolating this point from these 4 points. You can do sort of like a bilinear interpolation. You can interpolate along the radial direction and then interpolate along this angular direction. And the reason for using polar coordinates instead of just using Cartesian coordinates for doing the interpolation is that we want to essentially scale the power of the impulse response, because power is going to essentially decrease with square of distance. So when you're in this coordinate system, it allows you to make sure that the power is correct depending on the distance that you're at. And so the interpolation is going to be done independently on the magnitude and the phase of the impulse response. And the phase interpolation is going to assume, phase interpolation is sometimes difficult because you don't really know what the true phase, the true delay is, but we kind of make assumptions that it's minimum phase in causal system. And so the interpolation is kind of straightforward. The magnitude, and so first, do the angular interpolation, then do the interpolation in the other coordinate. And then the main thing is that you want to make sure that the power, decays with the square of the distance. So the main thing here is just that in this coordinate system, we can scale the power correctly. And so the overall scheme is pretty straightforward. And essentially the results I'm going to show is that we measure, so for a given distance, I'm going to show results. So you measure the actual response at 3 different angles, okay? And you interpolate the middle one using the other 2. And then we're going to compare the true measured response with the interpolated response. And so here's the results. So this is for the left ear, this is for the right ear. And the left column is essentially the impulse response. The right is the frequency response. Basically, I show the true response is this dark blue line. And using the frequency domain interpolation technique is this pink line. And using the time domain interpolation technique is the is this light blue line. And the main thing to see here is that time domain interpolation has so basically from the time domain response it looks like it's working pretty decently. But if you actually look at the frequency response, doing of course the frequency domain interpolation gives you much better results actually. And if you actually compare the SNR between the true impulse response and the interpolated one, the frequency domain interpolation technique gives you almost 9 times the signal to noise ratio as doing the temporal domain interpolation. And yes?
I notice in this case, the sample point is rather sparse.
Yes.
Right? There's only basically a few points in
right,
there. I assume part of that is measurement difficulty.
Right, right.
Can you do this? I mean, instead of moving the sensor, can you just rotate basically either the human body or the dummy head? Then you can have a much dense angular resolution.
Right, so that's one way of doing it, right. So I think to get sort of a perfect reconstruction, the theoretical results show that you need to at least measure almost at every, 5 degrees or something like that. And so although I presented the results for the spatialization, you can also apply the same interpolation techniques for the crosstalk cancellation, because that also involves measuring the room response and the HRTF. And the final thing is that if you're already in the frequency domain, it's very easy to actually do the spatialization itself using overlap add methods for convolution. Okay. So I actually have a demo, to kind of rotate, but we haven't done any user studies. But I have a demo to kind of simulate moving around. So basically like the listener is in a particular location, and let's say the sound source moves in a particular pattern around the room. And so you need to wear headphones. I can play it here, but I don't think you'll get the effect. But I can, if anyone's interested, I can show it offline. I need to get the headphones for that. Yeah. Yes.
So the main reason for doing this combined thing is to reduce the number of measurements, or what is the main reason you're doing combined instead of separate room and head impulse responses?
So I think one of the main things is it gives you a more realistic sensation of the actual room rather than modeling the room.
Supposing you measured, measured at a point in the point microphone, on the directional microphone, sound source in the room. You just move the sound source around and measure, so you get a room impulse response.
Right. Oh, so you're saying measure the room response and use HRTF separately. Yeah. So one thing, another reason to do the combined thing is that there's a complexity reduction when you do the combined impulse response. And if you look at so I think one of the main things was that once you do the combined response, you can actually break up the filter pretty easily into a very short tap filter, which is independent of position and direction. So so the short tap filter is dependent on position and direction, and the tail of the filter is essentially independent of position and direction. So it gives you a big complexity savings when you're actually doing the convolution.
Isn't the short one just the HRTF?
Yeah, the head is already really short.
Right. So, but the room response also you can break it up into 2, right? So you can break the room response into the long tail and the short tail. Okay, so the next one is a depth map codec scheme, and this is essentially a very low complexity real-time codec for coding depth maps, and it and the main advantage of this is yes.
Camera for this
Yeah,
business.
I saw that. So the main advantage of this is that the complexity is extremely low. You can encode and decode a frame in at the rate of almost over 100 frames per second. And the other advantage is that it gives you compression ratios which are actually significantly better than JPEG 2000 lossless mode, as well as JPEG XR lossless mode. And it's not to say that this necessarily the best depth map codec, but it's a very simple, bufferless. It requires just no frame buffering. So depth maps are very are becoming more and more common in media processing, and there's examples of cameras such as Kinect and time-of-flight cameras, and depth maps themselves are very useful for many tasks. Processing tasks such as foreground-background segmentation, activity detection, and also for rendering alternate viewpoints. So you capture a view from a particular location, and you capture the depth map, and you can use that to reconstruct alternate viewpoints. But the main drawback is that if you're actually going to transmit a depth map is essentially 16 bits per pixel, and it's very, very costly to transmit a depth map. And we wanted to kind of develop a depth map codec which is extremely low complexity, doesn't require any frame delay, so no prediction across the frames. And although you don't want to necessarily lossily code a depth map in the same way you lossily code an image, because the final thing that you're consuming is not the depth map itself, but the depth map is perhaps being used to do some other task. And so instead of doing lossy compression, a simple thing is just to do lossless to near lossless compression, so that you don't necessarily lose any fidelity when you're doing the task that you want to do. And of course, we wanted to make sure that it gives you much better compression ratio than existing schemes. And so here's an example of a depth map, and each pixel is essentially 16-bit. But the thing to note is, of course, there's very, very high correlation across pixel values. And another main thing is that the sensor accuracy actually decreases with depth. So if you're actually measuring the depth, which is twice as far as some other depth value, then the error in the measurement is going to be 4 times as large as the error that you would get in the closer values. So the further out you go, the less accurate the sensor gets. And this essentially means that, if the sensor is less accurate, why code it at full fidelity, right? So essentially, you can quantize the values that are further out without losing any accuracy. So the codec essentially consists of 3 components. One component takes advantage of the last fact that I said, which is that the sensor accuracy decreases with distance. So instead of coding the actual depth, you code inverse of depth. And essentially, you pick A and B. If you pick A and B properly, you can actually maintain the full fidelity of the sensor in your coding. And if you actually choose A and B, slightly, off, then you can actually do some minimal quantization of the depth values also. So like if A is smaller than it needs to be, you're actually going to, end up quantizing the depth value. And the main thing is that, you don't need to know how this actually works, but the main thing is there's going to be a parameter which you can control, which controls whether you're lossless with respect to sensor accuracy, or you have introduced some amount of loss, some small amount of quantization loss. And the other thing, of course, was that there's very high correlation between pixels. So, you can essentially do a one-step simple prediction. And then once you do this prediction, you end up with long strings of zeros. But the long strings of zeros, you don't know. You don't want to pre-decide a distribution on zeros or anything. So a very effective technique to code the output of that is to use an adaptive run-length Goulomb-Rice code. And this is a very low complexity lossless entropy coding. So I'll just talk a little bit about the adaptive RLGR code. I mean, the details are that this is an adaptive scheme to code. If you have a long string, there's many zeros, and then there's a level, and then there's a long string of zeros, then there's a level. But sometimes you may have a long string of non-zero values as well. So sometimes and so the way it kind of works is you operate in one of two modes, a run mode or a non-run mode. So in a run mode, you expect there to be long strings of zeros. And there's a parameter which tells you how long of the string of zeros you expect. And in the no-run mode, you kind of are just coding levels themselves. And so in no-run mode, each symbol just gets coded using a Goulomb-Rice code. And in the run mode, you code the string of zeros using some symbol, and then you code the level. And the other nice thing about this is that you don't pre-decide your distribution of zeros, and you kind of learn it as you go along. And so what I'm going to show is I'm going to basically show you the compression ratios and encoding, decoding time for this codec. And I'm going to code two sets of depth maps. One set is slightly more complicated because it actually has a large range of depth values. So this left one, even the background has depth values. In this one, in the right one, this is a simpler set. And the reason it's simpler is that a lot of the background values are actually out of the sensor range. So they're actually all coming up as 0. So there's less information to code here. And I'm going to compare 5 methods for coding. One is basically just numerically lossless. There's absolutely no loss between the original and the coded. And the way you do that is that you essentially don't do the inverse coding. Okay. The next one is, this is essentially lossless with respect to sensor fidelity. And then there's 2 more which are slightly lossy. They're pretty close to lossless, but slightly lossy. And then I'm going to compare the compression ratio with JPEG 2000 lossless mode, so I tried many different codecs, JPEG 2000 lossless, JPEG XR lossless, PNG, and many different things. And actually it turned out of all those, this was the one that actually performs the best. And so here is the compression ratio for this set 1, which is the one that's more complicated. So this is the numerically lossless coding. So, you get about a 5-to-1 compression numerically lossless. And this is, essentially lossless with respect to sensor fidelity. You get about 6-to-1. And these are slightly lossy. And even with slight quantization, you can get pretty good compression ratios of 15-to-1. And as comparison, JPEG 2000 compression ratio is under 4. This is the lossless mode of JPEG 2000. And these are median results, and even the max 90th percentile results are not much worse than this. And here's the encoder speed in milliseconds, decoder speed in milliseconds, and this is for set 2. So set 2 is much simpler to code, and in this set, you can see that even numerically lossless, you can get about 13:1 compression. And even with slight loss, you can get 35:1 compression. And JPEG 2000 lossless is under 10. And this set is actually very easy to code. So in about 7 milliseconds, you can encode and decode a frame. And then, so if you do numerically lossless, then any processing you do with the depth map is going to be identical to the uncoded one. But what I want to show here is that even if you do, let's say, lossy coding of the depth map, okay, or near lossless coding of the depth map, what I want to show is that processing is unaffected by this small amount of quantization. So the way I do that is that we capture a view from multiple viewpoints. So we have essentially, I guess, many cameras which are capturing the same scene from many viewpoints. And this is the viewpoint, one given viewpoint. And this is the depth map corresponding, and all the cameras are calibrated. So this is the original viewpoint, this is the uncoded depth map, and this is the coded depth map with a slight amount of loss. And this is an alternate viewpoint. So basically the viewpoint before. So this RGB map and this depth map are used to reconstruct another viewpoint. And this is the original that you capture from that other viewpoint. And this is the reconstruction you get using an uncoded depth map. And this is the reconstruction you get using a coded depth map. And the results you get from using the coded depth map versus uncoded depth map are pretty identical. And this kind of just shows you the PSNR when you're reconstructing 5 different viewpoints. So this, and they're kind of concatenated back to back, actually. So this is viewpoint 1, viewpoint 2, viewpoint 3, viewpoint 4, viewpoint 5. And this essentially compares the original capture with the reconstruction you get. And this is basically using lossless and some amount of loss. And basically what you can see is that even if you code the depth map to some small quantization, you effectively don't hurt the reconstruction at all. You get the same reconstruction as you would if you use an uncoded depth map.
This is PSNR of what?
So this is the PSNR between the original capture and the reconstructed. And reconstruction is done using another viewpoint. Yes, with the RGB.
Okay.
Yeah. Right.
Is my impression of the 750 is better than lossless?
Yeah, 750 is slightly better. But it's. There's no. Let's put it this way: the reconstruction itself is not 100% accurate, right? So, you could go either way when you code it, right?
Measured view?
Yes. Yeah, ground truth is measured view. Yeah.
So that error is probably larger for the coding.
Yeah. Right. And this is showing you this is comparing the reconstruction using an uncoded depth map with a reconstruction using a coded depth map. And, at various quantization. So, with near lossless, it's almost the same. And even with this, this much amount of quantization, the results are, the PSNR between the reconstruction is not that bad. And basically, the conclusion is that it's very low complexity codec. And it gives you better compression than existing, lossless coding schemes. Okay. Yes.
So I can kind of accept the fact that the depth values were linearly correlated, between different pixels. But when you take the inverse of that, do you think that's?
Well, actually, they're pretty much identical. That's the thing. So, the Kinect sensor, the data coming from the Kinect sensor actually has identical values for neighboring pixels.
Slight variation, there's a board that's going away from it, and the depth values are perfectly linearly related to each other. After the inverse transform, are they still maintaining a linear relationship?
So it won't be a linear relationship, but it would be, I mean, it may be a monotonic relationship.
So the VCA would look better on the original samples than the inverse samples, right?
Right, so you're saying essentially the inverse will amplify the difference between two successive values. Yeah.
But the sensor data is not that way. It's the sensor noise.
So I mean, the thing is, I think the Kinect sensor itself is probably doing some sort of filtering too.
Longer range, you see the effect, but if I just show my computer monitor tilted away from the sample, within a foot or two, the quantization error is almost the same. No? What is the curve? What is the curve?
It's increasing in
Square root.
But I think the main thing is there's also some amount of filtering going on with the data coming from the sensor itself.
This is the early Kinect sensors. I thought you guys get a newer sensor.
Yeah, we have also newer sensor.
What is the noise level in the newer sensor compared with the old sensor?
So Kinect sensor and data sensor, they have a similar.
They have similar noise characteristics?
The
Kinect style would be different.
Because I
We're
think
talking
the
about
time of flight
no, time of flight is different. This is for Kinect.
And if moving to the future sensors, I mean, is, for example, the inverse transform, I mean, did that noise relationship still stands?
For Kinect, for time of flight, probably will not apply.
You mean the noise level?
Noise level, yeah, the noise level is different, yeah.
I think there's other ways to do quantization, even if you don't do the inverse coding. Even without the inverse coding gives you an additional 30% or so.
I think the inverse coding still basically benefit because, I mean, if you're far away, the importance of accuracy is less.
So I think essentially it's like a non-linear quantization, right? So the further out you go, the bins get larger, right?
That was my question. Right? What would you
Did you try to do frame difference in any other temporal prediction?
No, but I imagine you would probably get. I mean, the gains may not necessarily be as large because many pixels can be again well predicted from the top. I mean, the previous pixel, right? So only probably the boundary pixels. Like if somebody, and even from frame to frame,
the whole background would disappear.
Right. What I'm saying is like the only thing remaining after this pixel differencing is essentially the edges, right? And the edges are likely to move anyway from frame to frame, right? Right. So, and the background is already pretty well zeroed out. So there may not be as much gain by doing frame differencing.
Do you plan to explore some segmentation to place in rows better encoding?
I mean, I think there's many ways that things like this can be improved, but the main thing again is like this gives you already like pretty good rate compression ratios, and it gives you encode and decode frame rates of close to 100 plus frames per second, and that's very important for any real-time application, such as if you're using this for video conferencing, you don't want it to do complicated things, right? You want to get as good compression as you can for very, very low complexity.
Okay, so let's thank Sanjeev again. So I'm going to talk about the ViewMark system. This is an interactive video conferencing system for mobile devices. And this is a joint work with my summer intern, Shu Shi from UIUC. Nowadays, it's very common, you have to join remote meetings from your home, your office, etc. And ideally, you want to have a similar experience as face-to-face with the remote participants. So this means you want to see what you want to see. You want to see who is talking. You want to see what's the reaction from other people. And from the audio aspect, you want to hear voice coming from different directions, so spatial audio, like what Sanjeev mentioned earlier. And also you want to share documents and objects with other people. So that's the ideal case. And this motivates some high-end telepresence room, like the Cisco telepresence room or HP Halo room. Okay. But this is very expensive. Each room costs about $500,000 US dollars. And another device which is much more affordable is Microsoft Roundtable. This device has 5 cameras which produce panoramic video. So if you put the device at the center of the table, then the remote person can see everyone around the table. And also there's 6 circular microphones around, and the microphone array processing can determine who is talking. So the device can send to the remote party the active speaker video. So here is the interface of the roundtable. So this is the active speaker window, and this is the panoramic video. And here you can share screens with other people. And more people are now using mobile device to communicate with others. And since mobile devices are always with you, so it's very easy to reach out or to be reached. And with iPhone FaceTime, more and more people now use video for communication. But the video on the mobile device is still pretty limited. So if you try to join a remote meeting room, it's probably pretty poor quality. So this is probably what the best you can get. It's very hard to see the speaker's face, and the content on the display is probably very hard, and you cannot see other people talking unless you ask other people to move the phone around. Okay. So it's not very immersive. Active speaker has to be done manually by asking other people. And there's no data presentation sharing with iPhone FaceTime. So to improve the experience of video conferencing over mobile phone, we developed this ViewMark system. And here I will show first the ViewMark system with the roundtable. So the mobile device is connected to a roundtable, and the roundtable has been modified so we can produce spatial audio. So it's not the standard roundtable gives you only a single channel audio, and we modify so we can get the spatial audio. And here is the interface of the ViewMark on the mobile device. You have this remote video. So as I mentioned earlier, the roundtable can produce 360 degrees panoramic video. But because of the screen size on the mobile device, you can see only a fraction of it. And I will describe this later, how to leverage the panoramic video. And you have a self video, which can be minimized in order to reduce the computation cost on the mobile device. And you can use a portion of the screen to share data with the remote room. And on the right here, this is a screenshot with the bookmarks. So when you feel a region of interest is interesting, you can bookmark the location, and later you can come back quickly. And that's more detail here. So what we do here is, since the roundtable can give you panoramic video, and you see only a portion of it. So one way is to use your finger, use the touch to move around and to determine which part you are interested in watching. Okay. Another way is to leverage the inertial sensor on the mobile device. Basically, you can move the mobile device around to see different parts of the remote rooms. Okay. And then if you see, okay, this is the location I want to watch probably later, you can tap on it and create a bookmark here. And you can create another one. Okay, so you can create as many bookmarks as you like. And then later on, if you want to go back to that location, you just double tap on any of the bookmark, and then you switch, you get the set view immediately, the live view immediately for that viewpoint. And also, our system can do the data sharing. If you are in portrait mode, then the data is shared from the low part of the screen. And if you tilt to landscape mode, then you have a full screen of the screen shared by the remote from the meeting room. And the data sharing software was provided by MSR Asia. And here I will show you a video of the system in action. So it's a live recording.
We are having a meeting here
of the demo.
Room. This is my round table, and I'm presenting some slides here. Some of my colleagues are joining remotely from mobile device and various other things, and we'll see how an experience with a mobile device looks like.
On my mobile device. I'm on the remote side. Let me connect with the mobile device. So you get the video. Here you see as a video from the remote room. And as you saw earlier, the remote room, there is a round table. So it's a 360 degrees panoramic video. So I can pan it around to see different people. Okay. Here, I see Rajesh, and I can see further, there are a lot of pattern cubes there. Okay. So I can bookmark different locations. Let's see. Pattern cube. I don't know why I bookmark the pattern cube. Rajesh. Okay, Zhichen. Okay. And later on, if I want to see Rajesh, I can double tap and immediately switch to Rajesh. Pattern cube or Zhichen if you want. Okay. And this is a video of myself, just to check how I'm looking like and meeting with the spatial audio. Okay, so of course we cannot demonstrate spatial audio. So here you hear voices are coming from different directions because we spatialize the audio. So really I feel very immersive to attend the remote meeting. And the next I will show you the data collaboration part, data sharing part. So this is the data from the remote desktop. And let's take a look at the full view here. Okay, so here you see the full screen of the remote desktop. I can move around, and you can see it's very visible. Okay, you see in the French word visible. Anyway, so that's the demo. Why I cannot? Okay, so we also connected the view mark with a new device called the spin top. So spin top is shown here on the bottom. It can spin with a programmable motor. This can be controlled from the computer. So you can see here we just put a laptop on top of the spin top device with camera, and you have a screen. So basically it can serve as a proxy of a remote participant. And the system works exactly the same way. Okay, the interface is the same, everything is the same, except now the panning is not choosing a particular view of a panorama video. Now the panning on the mobile device will control physically the spin top device. So you can move around remotely, okay, to control the device. This gives the remote person a lot of control. So in summary, the ViewMark system gives you a two-way interactive audio-video conferencing experience, and it's immersive with binaural spatialized audio. And the mobile user can control the video stream to view different parts of the remote room, and you can bookmark viewpoints of interest and switch view quickly. And you can also have the active speaker view provided by the roundtable device. And you can share screen and display. And in perspective, the system can be improved in a number of ways. For example, currently the view marks are arranged sequentially depending on when you tap on it. Ideally, you may want to have the view marks arranged in a consistent way with the physical location. Okay, and the second possibility is to do the face detection, active speech detection also. So you can have a suggestion from system who are the active speakers, possible speakers. So you don't need to tap on the device. So it can be automatically populated as some bookmarks on the mobile device. And now if you move from the mobile device, the small smartphone, to a tablet, which has a bigger screen, probably want to have a better UI design. And here's an acknowledgement. We have received quite a lot of help from different people. And thank you for your attention. Yeah. I just finished 2 minutes before the end of questions.
So you mentioned about using face detection to smartly manage that. So what if even by that time you use the detection, you locate the location, then when you come back to that view, the person has moved?
That's possible. Then you need to update, yeah. If you can track the person, then you can update the location automatically. So because of the view mark, is what it saves is really the location. So in the spin top case, is just the angle of the device. Right? So that's it can be updated depending on the face detection and tracking.
So the spin top itself, it's intended for like a substitute for a random view.
Yeah, it's like a proxy, right? Physical proxy of the remote person. So you can put the spin top on at the end of the meeting room table, right? Okay, so thank you very much, and bye-bye.